So, welcome to this class on hardware security. So, today we shall be continuing our discussions on power attacks. In particularly, we shall be talking about a new type of power analysis, which we essentially have not been discussed before, is what is called as template attack. So, it is basically a form of simple power attacks, and essentially I would say like is one of the most powerful forms of side channel attacks. Okay. So, we shall be discussing about a multivariate normal distribution, for formulation or formalization of noise, which is very central to understanding the template attacks. We shall be discussing about correlations in power traces, and finally, on maximum likelihood decision rule, which we use to determine the key in case of template attacks. I shall be talking about some numerical instability problems which can come up because of the formalization of template attacks, and discuss about a technique which is called as reduced templates to remove it, and essentially conclude with like a modification of the basic template analysis, which is called as the least square test or LSQ. So, to start with, as I said, the template attacks is like one of the strongest forms of side channel attacks, where we require an adversary to have access to an identical experimental device, so that he can program to his choice. Basically, he can give inputs, he can vary the key. Okay, so, he can basically pretty much play around with the device. Now, the success of these attacks relies on the ability to model noise. Okay, like as we have seen, like in the previous side channel attacks, right, the noise was a deterrent, because noise essentially was reducing the SNR or the signal to noise ratio, which was adversely affect the success rate of my attack. But here we will take a different approach. We will basically try to kind of model noise in a very accurate manner, and hence we will try to use it to extract maximum knowledge about from every sample. That means, from each sample we will be trying to estimate very accurately the noise, and from there we will be trying to estimate or extract maximum knowledge. Okay. And that is why the final attack can be done with very few traces, probably even ideally with only one. Okay. And it can threaten countermeasures, because many of the countermeasures are developed with this assumption that the attacker will not have access to significant number of power traces, but as in template attacks we require very few, ideally probably only a single trace. Therefore, many of these countermeasures can be challenged. Okay. So, therefore, right, this brings us to the modeling of noise. Like till now we have been looking at noise, right. Essentially, we have been focusing about every point in the trace, in the power trace, and we have seen, right, that electronic noise essentially at that every point was kind of having a Gaussian distribution that we discussed in the previous class. So, basically we were like looking at every point in a discrete manner. Okay. But on the other hand, if you look or think about it, right, electronic noise at every point of the power trace, though it is normally like it is kind of normally distributed, but they are not completely independent of each other. So, what I mean, like if you look at adjacent points or time instances in the power trace, then there may be correlations for noise. Okay. And that essentially you can imagine, like suppose you are processing like you are doing an AES operation or some kind of transformation inside your chip, then successive time instances, right, will essentially have essentially you are kind of, you can think of like you are basically doing the same operation and you are distributing it over time. Okay. So, therefore, right, for example, it may happen that you are doing an operation over r rounds, okay, and inside the round there are again some sub operations which you are doing across clock cycles. So, therefore, right, you can imagine that suppose you are doing a multiplication which is kind of spread across clock cycles, then you can expect that there would be correlations in the computations that you are doing. Okay. So, this is the signal part of the power trace, but the interesting thing is that even the electronic noise at every point of the power trace, right, essentially there is an amount of correlation between them. Okay. Whereas, if you take two distant points, then the correlation between the power traces are expected to be less. I mean the correlation between the noise components are expected to be less. Okay. So, therefore, right, this brings us to this multivariate normal distribution of modeling of the power trace, where and it is basically a generalization of the normal distribution to higher dimensions. Okay. So, it can be described by a covariance matrix and a mean vector M. So, in the previous case, right, we are basically looking at every time instances, and we have seen that mu and sigma were used to characterize it. Here, since we are looking at multiple time instances, so rather than processing on one single scalar mean value, we will be basically processing on a vector mean of or a mean vector. Okay. And also a covariance matrix. So, basically, right, I mean this brings us to this formalization or probability density function of the multivariate normal distribution. So, you can see that f x is equal to 1 by square root of 2 pi whole to the power of n determinant of C. So, C is the covariance matrix here, and m is essentially the mean vector. Okay. So, you can see that we have written e to the power of minus half x minus m. Note that x is essentially also a vector. Okay. So, you are basically doing a vector subtraction, and then you are multiplying it, like you are basically doing a transpose, and you are multiplying it with the inverse of the covariance matrix, and you are multiplying this with the vector x minus m. Okay. So, therefore, right, basically the idea is that you have got certain points of interest, like suppose maybe suppose as an example, think that suppose we are observing in the power trace 10 time instances. Okay. So, therefore, previously we were looking all of them independently, but now we are trying to process them as a vector. Okay. So, therefore, you can imagine that if I have got in my power trace, for example, like this, like suppose this is this is the power trace that I have, right, and I observe different time instances in a window, okay, in a window of time. So, suppose this is my total window of operation, okay, and I am observing the corresponding power values, which I denote as say x1, x2, x3 and so on till x maybe xt, because suppose, or maybe xn, like if n is my total window size. Okay. So, therefore, right now this stands for my vector x, this stands for my vector x. Okay. And I basically find out the mean vector also in this fashion, because every time instance right here is now also is essentially a statistical distribution. So, we basically take the mean of every point, right, and then that gives me my vector. I mean, that gives me my vector or mean vector, and I also similarly calculate the covariance. So, the covariance basically, as written over here, is basically the covariance of the points at index I and j. So, therefore, right, if I observe say here there is a time instance, suppose the time instance is I and there is a time instance say j, then covariance of xi, and so this brings us to the definition of the multivariate Gaussian model. So, this is a generalization of the normal distribution that we have already seen. So, here you can imagine that we rather like observing a single point of the power trace are essentially observing a window. So, we are basically observing a window of time instances. So, therefore, that means like suppose this is my power consumption. So, these are previously we were observing like at one time instance, which was my point of interest, but now I am observing a window of time instances. So, therefore, this is my corresponding window. Okay. So, therefore, every time instance you can imagine that this is like x1, x2. So, these are like the various samples that you are getting at different time instances. So, let us write x1 to xn to xn for example. Okay. So, this basically makes my vector x, this is my vector x. Okay. So, therefore, what I now do is basically I calculate the mean at every point. Okay. So, every point basically when I am varying it, I am basically getting different values at that point, and I take a mean at that point, and therefore, I now get a mean vector. So, previously I was getting only one mu value. So, now I am getting a mu, I am getting a like a mean vector. So, this mean vector is essentially denoted here as this m value, and now and also right along with it we basically find out, we also want to kind of find out the covariance at different between two time instances. For example, suppose xi is one time instance and xj is another time instance, okay, and I want to calculate the covariance between these two time instances. So, that essentially is basically denoted by Cij, and therefore, you can imagine that I can basically make a matrix, right, which I called as the correlation matrix, where all these values Cij basically stands for the correlation, stands for the covariance between two time instances I and j. So, you can imagine that like this would be a symmetric matrix, because Cij and Cji would be same, and therefore, this matrix would be essentially a symmetric matrix. So, therefore, in this fashion, right, I can get the mean vector m, which basically lists the mean values mi, which is equal to exi for all points in the curve, and you will also have C, which is essentially nothing but filling up the covariance matrix. Okay. So, when filling up C and M, like if I get the value of C and M and then plug it into the equation, then the PDF or the probability density function of the vector x is returned. So, therefore, when I am observing a power trace, so this power trace is say called x, I basically get the corresponding PDF or the probability density like function for this vector x is basically returned. For any given vector x, you can calculate that by just plugging in this and calculating this value. Okay. So, that is essentially the background behind the multivariate Gaussian modeling. And now what we will try to do is we will basically try to observe this for a real power trace. Okay. So, this is a case study that we did when you basically implement say an AES algorithm or AES architecture on a Sakura board, as we have seen in our side channel setup. And now we see that electrical noise, right, really does not significantly change from one point of the power trace to a subsequently close point. Okay. So, what we do here, we basically can easily study this by something which is called as a scatter plot. So, in the scatter plot, in the x axis we point like the say the amplitude, for example, which essentially basically I am taking two close points A and B, and we are trying to plot the amount of power which is consumed at two close points. Okay. And you can see from this scatter point, right, I mean there is a kind of correlation which you can observe that which essentially can be modeled by essentially a straight line. So, ideally, right, there will be a very you can see that there is a correlation, and if you get the best fit, for example, you will find that there is a line that you can draw over here, and you can understand there is an amount of correlation. Okay. So, this correlation, right, is essentially as like the covariance basically is also another way of measuring this dependence. Okay. So, therefore, right, we observe that electrical noise really indeed does not change across close by points. Okay. And the electrical noise that is present in neighboring points is therefore typically quite related. There is an amount of correlation between them. But if you observe the same thing over like far off points, for example, you find that correlation has been destroyed. Okay. And you can indeed observe this, that like what we have done is basically, if you see in this plot, we basically measured the correlation. The correlation turns out to be something like 0.5, which is quite high, and if you compare it with this correlation, it is something like minus 0.01, which is quite less. Okay. And therefore, you can indeed understand that when you are taking two far off points and you are trying to correlate the amount of power consumed, then there is less dependence across them. Okay. So, this essentially gives us a good amount of understanding about how the noise behaves across time instances, and basically gives us an ability to model the noise. Okay. So, therefore, this like the covariance or correlation are therefore statistical tools to measure the linear relationship between 2 points of the power trace. And as we know that covariance of x comma y is nothing but E of x, or the expectation of x y minus E x into E y, and that essentially can help me to estimate the covariance. Okay. And likewise, right, you can also calculate the correlation coefficient, and correlation coefficients essentially are nothing but giving us the ability or measure the linear relationship between two adjacent points in the trace, like covariance. Okay. So, typically, right, as we know that the like the correlation, for example, can be found out by this formula, which is nothing but the covariance of x comma y divided by the square root of variance x and variance y. So, the covariance of x comma y is estimated by this numerator, which is like sigma I equal to 1 to n xi minus x bar into yi minus y bar, okay, divided by the square root of the variance or the product of the variances. Okay. And this you can observe that like that if I basically take in this formula and I calculate the correlation, then this correlation is quite small when I am considering two far off points in the power trace. Okay. Whereas, if I take two successive points or two close by points, then the correlation is quite high. Okay. So, you can see it is something like 0.5, okay, which is pretty high. So, on the other hand, right, you can observe that the covariance also kind of gives you the similar estimation. So, you can see the covariance is something like minus 0.36. So, it kind of tells that it is kind of negatively correlated, but if you see the absolute value also, the covariance is much less compared to here, where the covariance is as high as 0.95. Okay. So, which shows that there is a more dependence when you are considering close by points. So, therefore, now what we will try to do is, with this background, we will be trying to look into the AES architecture and try to see how we can build the template. Okay. So, for this, right, we will basically again look into the AES architecture. So, this is nothing but a recapitulation of how the AES works, right. In fact, right, we will be considering only at the first step, where I am basically taking the plain text, I am doing an addition round key with the key. Okay. So, basically what I mean is, I am basically concentrating on the first part, where I have got a plain text P0. So, this is like there are other parts of the plain text, but I am concentrating only on the 0th byte. Okay. And I am XORing it with again like like 16 bytes, but I am again focused only on the first part, which is my K0. Okay. That is the first part of the key, and I am trying to basically build templates.
So what I do is we basically keep the plain text same and vary, say, the first byte of the key matrix K0. Okay, so we basically keep this P0 constant and we basically vary this part of the key. So basically, right, I mean this K0 can take 256 values, but rather than dividing it into or building templates of like 256 classes, we basically make templates depending upon their Hamming weights. Okay, so therefore I will have 0 to 9 or 0 to 8 possible, that means 9 possible Hamming classes, and depending upon the Hamming weight of K0, I basically form individual templates. So you can easily understand that there will be 9 templates, but there are some templates where there are more values possible compared to the other ones. For example, right, if I just tell you that the template, that the Hamming weight is W, the number of instances which will basically fall into that template class, right, is 8 choose W, okay, which is not same if I vary W. Okay, for example, if the Hamming weight is 0, then there is only one possibility, which is all 0. Likewise, if the Hamming weight is 8, then again there is one possibility. But if there are like if the Hamming weight is 1, then there are 8 possible choices. Okay, so therefore this kind of varies, and therefore the number of, so this estimation is not, I mean right now like since you have got different amount of samples, right, it will not be exactly accurate, but we will see that we will try to take this as an example to understand the basic concept of how to build templates and how to apply template analysis. Okay, so now what we will do is basically we will keep on we will keep the plain text same, say and basically try to build templates in this fashion. And so what we will do is basically we will take this and try to create templates in this fashion. So we target, say, the key sorting step by keeping the plain text byte P0 constant and changing the other 15 bytes. Okay, so basically we need large number of samples to create the templates. So we basically vary the remaining 15 bytes of the plain text, but we keep P0 constant. So we keep P0 fixed. Okay. For each template, again we keep K0 from a Hamming weight class. Say, suppose I choose K0 to be from the 0 class. Okay, so that means K0 is held to 0, whereas the remaining 15 bytes of the K0 I can vary at my I can vary. So now therefore we target the first byte of the, so basically we have the power trace, and we know that we probably have an understanding about like when the first we basically target the first part of the power trace, because we know that there the add round key is participating in the underlying computation. You can of course make this process more systematic, but at this point I am assuming that we have a kind of knowledge about this fact, that that when in the power trace this component is coming into play. So now we just choose arbitrarily 10 time instances, again this is an important choice, and calculate the mean vector m, which is equal to m, and the covariance matrix which like C, which takes the value of C, okay, or small c. And therefore for every P0 K0 choice, so you understand that I am like holding up P0 to a fixed value, and I am taking different values of K0 depending upon the Hamming class W, and then I am building templates. Okay, so all these templates are essentially defined by this parameter of m and c. So therefore they are kind of defined by this parameter of m and c, which I have already defined denoted. So m is again the mean vector and c is the covariance matrix. Okay, so therefore I basically build template for K0 which belongs to different Hamming class W. Okay, so the different Hamming class W means there will be 9 possible templates in this fashion. Okay, so let us try to see an example to understand how it would look like. And for example, this is that so I am talking about 2 templates here. For example, in the first case you have a Hamming weight 0, that means it is all 0, and in the second case I will form a template where the template essentially the K0 will have a Hamming weight of 4. Okay, so there are 8 choose 4 possible things. So therefore here you can observe that the first thing in the template is a mean vector. Okay, so mean vector would essentially has got 10 points because I am observing 10 time instances in the power trace. Okay, so this is my mean and this is my covariance matrix. Okay, so this is my corresponding covariance matrix. You can observe that it is symmetrical. Okay, it's symmetric matrix. So basically we get a covariance matrix like this. We again make a template for Hamming weight 4. So this is my the template for Hamming weight 4, and I essentially keep these 2 things as my templates. And now I basically go to the attack phase. So in the attack phase, right, the attacker essentially will use the previously done template characterization to identify the unknown key bytes from a power trace from the device under attack. So that means you have now the device under attack which has been given to you. Note that you don't know the internal key now because the key is unknown to you and you need to determine. So I am assuming this at this point, right, that what I will do is basically I will try to get a power trace from this device under attack, and then I will try to correlate or match with my existing templates. Okay. So, this means that we basically what we will do is we will evaluate the probability density function or the PDF of the multivariate normal distribution, and which is essentially denoted as m comma c suffixed by p0 and k0, and the power trace of the device under attack. So, basically I have the template m comma c and I have a power trace which I denote by say the vector t. Okay. So, the vector t here denotes a given power trace. Okay. So, therefore, what I mean is that now you have got like this power trace. So, this is my corresponding power trace which is denoted as t, and this is my corresponding template. Okay. And I am trying to basically I am trying to fit it into the multivariate normal distribution formula, and I am trying to understand how much close is it to the actual template. Okay. So, basically here I replace, in one case I keep that like this t, and I kind of evaluate this function with a given value of k0, that means the template for k0. I again reevaluate this, I re-evaluate this for with with the template for say k1. Okay. So, therefore, right, what I do is we basically given a power trace t of the device under attack and a template m comma c, we basically compute this by just plugging, instead of x we plug in t. Okay. So, instead of x we plug in the value of t here, and note that t is basically accumulated by keeping basically the trace that you are accumulating, we are basically getting it by keeping p0 say fixed and choosing arbitrary values for the remaining 15 plain text bytes. Okay. So, the remaining plain text 15 bytes I am not bothered, but I am assuming in this case that I have got kind of a control on the input, but I do not know what is the internal key and I have got no knowledge about the secret key. So, the key is unknown here and we have got no handle on that. You can easily like generalize it to a setting where you do not have access to the input. Okay. Although I am assuming here that I have got an access to the input by like targeting for example the output of p0 comma XORed with k0 and building template at that point. So, in that case, right, just the knowledge of p0 will give you the corresponding key value. Okay. So, therefore, right now I am just like doing the template in this fashion, but you can generalize it to a scenario probably where you do not have access to the input even. Okay. But you know the input, of course. So, therefore, right, I mean so therefore with this background, right, what we do now is okay. So, let me clear this up. Okay. So, now what we do is we discuss a rule which is called as the maximum likelihood decision rule, which is basically the decision rule which maximizes the probability which essentially like gives me the potential candidate for the key byte k0. Okay. So, for example, right, we have developed a template for say k0 where the Hamming weight is 0, and we have like found out the we have also created a template where the Hamming weight is say 4. Okay. And that is denoted as k1. So, k1 would stand for all those keys whose Hamming weight is 4. So, now I take a power trace t and if I plug it into this formula, and if I get that like this is greater than this, then the maximum likelihood decision rule tells me that the key byte which I will return is k0 over k1. So, I basically have a preference for k0 compared to k1. Okay. So, therefore, right, let us see what happens with our case study. So, we basically have an unknown key which has a k0 value of Hamming weight 4 in our case, and we compute the probabilities as mentioned with respect to the template for 0 and 4. So, we basically observe a power trace for the template for 0 key, and we basically develop the template for 0 and 4 as we have already discussed in the previous class, in the previous slide, and then we observe we basically take the power trace for the unknown key, which essentially in this case has a Hamming weight 4, and we calculate the two probabilities, right. We basically in one case calculate the likelihood with respect to 0, and in other case we calculate the likelihood with respect to 4. Okay. So, you see that the likelihood with respect to 4 is more compared to that with 0, indicating that like it is more likely that the k0 will have a Hamming weight of 4, which is essentially the correct result. So, if you repeat this, right, for few more runs, for example, you still see that that this probability is more than this probability, indicating that indeed this is probably the most preferable candidate, and likewise for another run also we get similarly consistent results. So, in all cases the Hamming weight 4 has a more likelihood from template analysis. So now there can be like some numeric problems which can arise in template analysis. So while performing the template analysis, we can get into two important numeric problems. The first problem is which is related to the covariance matrix. Okay, as we know that we have to basically calculate the covariance matrix, and the covariance matrix, right, will essentially the dimension of the covariance matrix will determine on the number of important items like important or the window size. Okay. So therefore, the size of the matrix depends on the number of important points, say n, and this must be chosen carefully. Okay. Because if you make it very less, then maybe you will lose information, and if you make it very high, it will be computationally quite complex. And there can also be problems arising out of the requirement of the existing of its inverse. Remember that we had a determinant C which needs to be existing, right, and therefore, right, that probably can, if there are some numeric problems, right, then I mean with respect to numerical inaccuracies and so on, like floating point errors and stuff like that, then you may go into a scenario where the inverse does not exist. Okay. Also the exponent, right, tends to be smaller and lead to inaccuracies, because you have an exponential factor, and if it becomes too small, then again there can be inaccuracies. So one way of alleviating this is basically you take the logarithmic of the value. So therefore, if I take the logarithmic of the value, and remember the probability is lesser than 0, lesser than 1. So then, right, it would imply that a template that now leads to the smallest absolute value of the logarithm of the probability will indicate the correct key. Okay. So in the previous case, right, the probability we were maximizing. So now if I take the logarithm, right, then it will means that I will have to look for the smallest absolute value. Okay. So therefore, if I take the ln on both sides, you see that this is my corresponding equation. So therefore, in this case, right, my decision rule will be that if I find out the ln of the probability, right, with respect to k0, like the template for k0, and if this lesser than this, then k0 is my predicted class. Okay. So likewise, right, I mean you can actually, this brings us to something which is called as reduced templates, which is to further avoid the problems with the covariance matrix. We actually set the covariance matrix to the identity matrix. Okay. So we basically make it identity. That means in a way, right, we are neglecting the effect of the covariances between the points in the window, and this template is what is technically called as the reduced template. So you can, if you just take this reduced template and you redefine this equation, then you see that we have removed C, because C in this case is identity, and therefore it has got no play here, no role here, and therefore this is the corresponding simplification that I get. Okay. So again, if I take logarithms because of the reason which I said, then this is the factor which you get. Okay. So therefore, right now, right, we'll again, so this method, right, is also called, which is where we are using these reduced templates, is also called as a least square test, LST. It is because the only relevant terms in the probability estimate is now the square of the difference of T and M. Like if you see the formula, right, you have got two parts, where this part is essentially has got no role over here to compare, but this is the most important part, which is nothing but the vector T minus M transpose multiplied with T minus M, which is pretty much nothing but the square of the differences. Okay. So therefore, right, essentially you are the idea is again, like if this is essentially lesser than this, okay, then you will basically vote for k0 as your predicted class. So if you now take this and apply again to our case study, again for the 3 trials that you have seen, you see that the Hamming weight of 0, I mean if you just compare, right, you will see that it is an interesting thing that initially, right, you got a wrong observation, right, you see that this is larger than this, but for the other runs you see that this is 36 compared to 57, this is 66 compared to 94. So therefore, I will probably vote for 4 as being the correct Hamming class. Okay. So note that we've got an error in this one of the trials, okay, which is also perfectly possible. So therefore, to conclude what we discussed, correlation across the points in the trace leads to a multivariate normal distribution of noise, and template attacks try to use this by accurately model the noise. Okay. And template matching is based on the maximum likelihood principle, and reduced templates help us in performing template analysis with less numerical stability. Okay. Some of the references that I have used for this discussion is something that you can also have a look. So this is the textbook. Essentially, it's also often commonly called as the DPA book. Okay, written by Stephen Mangard, Elizabeth Oswald, and Thomas Popp. And there are some other references like papers which you can lead to, with the classic paper on template attacks, which is published in Chess in 2002, and followed by a note on practical template attacks by Christian Rechberger and Elizabeth Oswald. Okay. So with this, I would like to thank you for your attention, and we shall continue in the next class. Thank you.